All right, in this video, we're going to talk about suggested homework problems from section 9.5, which covers the alternating series test and tests for absolute convergence and conditional convergence with alternating series. Let's first talk about what an alternating series is. An alternating series has a sign changer that's either in the form of something like -1 to the n or -1 to the n plus 1, or something like that in the problem that makes the terms alternate from positive to negative and negative to positive in some pattern. It might be every other term, it might be every third term, something, but there's a pattern to the sign changes. Some of the terms are positive, some of them are negative. And all the other sequences that or series that we've talked about so far, we usually have had only positive terms for what we're dealing with. So let's go ahead and look at our first question here for alternating series. An alternating series does not meet the first condition of the alternating series test. What can you conclude about the convergence or divergence of the series? And explain. So easy answer here that this is going to diverge, and we know that it diverges because if it fails either condition of the alternating series test, it diverges. So there's no ambiguity here with the alternating series test. We know that as soon as it violates one of the conditions, we're done. So what are those conditions? So ignoring the sign changer portion, condition 1 is that it passes the nth term test. And condition 2 is that it is decreasing. That's it. So if we take the absolute value to ignore the sign changer, that it needs to go to 0 and it needs to be always decreasing, then it's going to converge. If it is alternating and it doesn't pass the nth term test, or it is non-decreasing, then it's going to diverge. So that's it. Let's go ahead and look at number 9. Number 9 says summation from n equals 1 to infinity of -1 to the n plus 1 over n plus 1. And notice the sign changer there. I could rewrite this one as it's the same thing as n equals 2 to infinity of -1 to the n over n. That'd be a little easier to see what's going on here because you know 1 over n diverges, the divergent p series. So it's going to pass the nth term test. It's going to be decreasing here. You know 1 over n is decreasing. Let's deal with this the way that it is though. 1 over n plus 1 is here. And we're going to go through 1, 1, and it's decreasing like this. The limit goes to 0 out here, and it's decreasing, so it converges. Right? Passes both conditions. Now, we haven't really discussed conditional or absolute convergence, but this series does not converge on its own simply because of the 1 over n plus 1 part without it being alternating. So I would call this conditionally convergent. to say that it's convergent on the condition that it was an alternating series. So that's what I mean when I say conditionally convergent. And again, limit as n goes to infinity of 1 over n plus 1 is equal to 0. There's my first check. And my second check is I can do this with a derivative. I can do this with a direct comparison, but I want 1 over n plus 2 to be less than 1 over n plus 1. And then this is n plus 2 greater than n plus 1. 2 is greater than 1. This is true for all n. It's an element of the natural numbers. So all n greater than or equal to 1, which is where we started there. So we're good. Let's go ahead and look at number 13. Number 13 says summation n equals 1 to infinity, negative 1 to the n, 5n minus 1 over 4n plus 1. So this is going to fail the first condition. Limit as n goes to infinity, 5n minus 1 over 4n plus 1 is 5/4 is not equal to 0. So this diverges. I don't even need to test the second condition. Let's look at number 17. Summation n equals 1 to infinity, negative 1 to the n over square root of n. So limit as n goes to infinity, 1 over root n is equal to 0. 1 over root n plus 1, is that always less than 1 over root n is, let's square both sides. That should maintain the truthfulness of this. If this is less than this, squaring both sides, because these are positive numbers, and then take the reciprocal, and then subtract. And because this is true, this is true, this is true, so on. So it passes. So this is conditionally convergent. Because it's conditionally convergent because if I would just look at 1 over n to the 1/2, that's a divergent p-series. So it's not convergent based off of this 1 over root n part. It's convergent based off the fact that it's alternating. Let's look at number 25. Summation n equals 1 to infinity, negative 1 to the n plus 1, root n over n plus 2. And did my instructions change at all? Nope. So limit as n goes to infinity, root n over n plus 2 is 1 over root n plus 2 over root n is going to be going to approach 1 over infinity plus 0 is infinity, so this is going to go to 0, so that's good for A. Then I want to look at square root n plus 1 over n plus 3. Is that less than square root of n over n plus 2? So squaring both sides should maintain my inequality here. So n plus 1 over n plus 3 squared less than n over n plus 2 squared. And let's go ahead and let's cross multiply, which again should preserve my inequality since everything's positive. So n plus 1 times n squared plus 2n plus another 2n's will be 4n plus 4 less than n times n squared plus 6n plus 9. So this is going to be n cubed plus 4n squared plus 4n plus n squared plus 4n plus 4 less than n cubed plus 6n squared plus 9n. And n cubes are going to drop off here, and then 5n squared plus 8n plus 4. Is that less than 6n squared plus 9n, so negative n squared minus n plus 4 less than 0, so n squared plus n minus 4 greater than 0. And that's going to be let's look for where n squared plus n minus 4 is equal to 0. N squared plus n is equal to 4. This is going to be plus a quarter, and plus a quarter is n plus 1/2 squared is equal to 17 fourths. N plus 1/2 is equal to plus or minus root 17 over 4. This is a number a little bit bigger than 1. N is equal to negative 1/2 plus or minus root 17 over 4. I'm going to throw out the minus part because that needs to be a natural number. So n is equal to negative 1/2 plus number a little bit bigger than 1 is what I'm interested in here. And so this is going to be number a little bit bigger than 2 is what I meant to say, because the square root of 4 is 2. So this is something a little bit bigger than 4. 4 divided by 2 is 2. So number a little bit bigger than 2 minus 1/2 is number a little bit bigger than 1/2. So let's look at my series here. Doesn't look right. Looks like it is maybe not so. At least not if I am dealing with 1 to infinity, but convergence and divergence doesn't change with the, if I would pull some terms off. So let me pull the first, let's say, this is going to be, what did I say, 2 minus something. So let's pull the first term off here, and that will be the same thing as square root of 1 is 1 over 3 plus n equals 2 to infinity of negative 1 to the n plus 1 root n over n plus 2. And now, because this is starting at 2 instead of at 1, negative 1/2 plus root 17 over 2. See, that's that means that I'm good. Once I get to 2, it should be decreasing from there. So this will meet the conditions for convergence. That single term there, or any finite number of terms there, won't change the convergence. So this converges now by the alternating series test. So that's good. If I kept going up and down and up and down, would be the problem for the alternating series test. If there was never a place where it was decreasing and it was always decreasing from that point forward. I could also have figured out that this was decreasing for all values greater than or equal to 2 using my first derivative test. So let me show you that. This is kind of nasty to use the first derivative test on, but I'll do it anyway. Square root of n over n plus 2 is f of n, and I want f prime of n is 1/2 n to the negative 1/2 times n plus 2 minus 1 times n to the 1/2 over n plus 2 squared, f prime of n. I'm going to multiply by 2 n to the 1/2, top and bottom. It's going to be equal to n plus 2 minus 2n over 2n to the 1/2 times n plus 2 squared is going to be f prime of n is a negative n plus 2 over 2n to the 1/2 n plus 2 to the second is equal to a negative n minus 2 over 2n to the 1/2 n plus 2 squared. And so now if I would go ahead and look at my first derivative here from 1 to 2, this would be a negative times a negative is a positive. Here, all these numbers will be positive, always down here. And then from 2 on will be a negative times a positive will be a negative. All these numbers in the denominator will be positive. So this is increasing from 1 to 2, and then decreasing from 2 to infinity. So I would need to pull off that first term since we started at 1 to make sure that I was decreasing from 2 to infinity. All right, let's look at this next one, which is 29. Summation n equals 1 to infinity of 2 times negative 1 to the n plus 1 over e to the n minus e to the negative n, which is the same thing as summation n equals 1 to infinity, negative 1 to the n plus 1, hyperbolic cosecant of n. And we're not going to really deal with hyperbolic cosecant so much. They just want us to know that that's the function that they're talking about. So limit as n goes to infinity of 2 times 2 over e to the n minus e to the negative n. It's going to be 2 over infinity minus 0 goes to 2 over infinity, which is 0, so check. And then b is going to be, and I'm going to use the first derivative test here like I just did a minute ago. So derivative at the top times the bottom minus derivative of the bottom times the top all over the bottom squared is going to be a positive and a positive together, that won't ever be 0. This piece down here could be 0, where e to the x is equal to e to the negative x. So that's going to happen when x is equal to 0, which is not within my range. So if I look at this thing here, for this will be a positive number and a small positive number, but this will always be bigger. So this positive number squared will always be positive. This will always be positive. This will be negative. This is going to be decreasing. So check. So f of n is decreasing on 1 to infinity. So it converges by the alternating series test. And again, they haven't really asked anything about conditional or absolute convergence yet, but they will. Just hang in there. It's coming. Now, 33 asked me to approximate the sum of the series by using the first 6 terms. So 33 says summation from n equals 1 to infinity, -1 to the n plus 1, 2 over n cubed. So I'm going to say that an is -1 to the n plus 1 times 2 over n cubed. A1 is, that'll be an even power, so that'll be positive. 2 over 1 is 2. A2 is going to be odd power, so that'll be -2 over 8, which is a -1/4. A3 positive power will be 2 over 3 cubed is 27. A4 is a -2 over 4 cubed is 64. So this is a -1 over 32. A5 is, it says the first 6 terms, so give me some more space here. A5 is a +2 over 125. A6 is a -2 over 6 cubed is 216, which makes this a -1 over 108. And I want to add these together and say that S is approximately 2 minus 1/4 plus 2 over 27 minus 1 over 32 plus 2 over 125 minus 1 over 108. It's 1.79. Let's call this 800. Let's go to 3 decimal places here. So if they went to 4 decimal places, that would be 7996. All right, that was 33. Let's look at 37, number of terms that we need to guarantee a certain margin of error less than 1,000th. So 37, we want summation n equals 1 to infinity, -1 to the n plus 1 over 2n cubed minus 1. So what I want is absolute value of s minus s, then some number here, which is going to be equal to the absolute value of the remainder, because the remainder is this, the difference here is the remainder. I want that to be less than or equal to a sub n plus 1, where this capital N is how many terms I need. So I want to keep going in my list until this term here is going to be then the margin. Let me just show you how I'm going to do this. So I want a sub n plus 1 to be less than 1,000th is really what I'm going for here, because that's what was given. So for getting the sign changer, I want 1 over parentheses 2x to the third minus 1. And I'll look at my calculator, auto starting at 1, going by ones. I'm just looking for the first time that we're less than 1,000. So right there, we are less than 1,000. So now let me prove this to you, that A8 is equal to AN plus 1. So n plus 1 is equal to 8, n is equal to 7. Let me show it to you with some other math here. So an plus 1, if I would stick this in, would be 1 over 2 times n plus 1 to the third minus 1, which is going to be equal to 1 over 2 times n cubed plus 3n squared plus 3n plus 1 minus 1 is going to be equal to 1 over 2n cubed plus 6n squared plus 6n plus 2 minus 1 is going to be equal to 1 over 2n cubed plus 6n squared plus 6n plus 1. And I need that to be less than or equal to 1/1000. So 2n cubed plus 6n squared plus 6n plus 1 needs to be greater than or equal to 1,000. And then subtract 2n cubed plus 6n squared plus 6n minus 999 greater than or equal to 0. And I graphed this with my calculator. So this is going to be 2x to the third plus 6x squared plus 6x minus 999, zoom 0, and second calc 0 of this function here. And so the next term casts this. So the ceiling of 6.93965 is going to be 7. So that's another way to find it with help from the calculator. We're going to do number 43 here. Summation from n equals 1 to infinity, negative 1 to the n over n factorial. And let's look at limit as n goes to infinity. 1 over n factorial is equal to 0. This is going off to infinity, so that's great. How about if 1 over n plus 1 factorial, is that less than 1 over n factorial? So let's ask if n factorial over n plus 1 factorial is less than 1. Because I should be able to multiply by this positive number and maintain my my inequality here. So let's divide as 1 over n plus 1 less than 1. That's true for all n greater than or equal to 1. Not going to be true for 0, but we aren't starting at 0, we're starting at 1. So this is great. We have met our second condition as well. So this converges. Was this alternating? Yes. Converges by the alternating series test, right? And that's enough for that one, but I want to tell you if it's absolutely or conditionally convergent. So let's go back and let's look at just this piece, 1 over n factorial, and I wish that we had another test that we don't have yet that works really well with factorials, but I want you to know that 1 over n factorial, well, I don't want you to know it, I want you to see it. X math number probability, there it is, factorial. And let's look at 1 over x squared. Just a simple p series that I know is convergent because I think that 1 over x factorial is going to be convergent. So let's zoom 6, and I can't even see the blue function. I'm going to zoom 0 to see if it will let me see what's going on here. I can't see it. So let me get really small here. Window 0 to maybe 0.25. No, 0 to 5. Say Wyman, I want to go 0 to right here because we're staying so small. Should be. Anyways, this is going to look. So let me go ahead and show it to you because n factorial is this list of factorials is for n is 0, it's 1, and then it's 1 again for 1, and then it's 2, and then it is 6, and then 24, 120, so on, right? So 1 over n factorial, if I look at my n squareds, this is 0, 1, 4, 9, 16, 25, and you notice that at this point right here, the n squared gets bigger than, I'm sorry, at this point right here, that n factorial gets bigger than n squared, and it's going to stay bigger. So that means 1 over n factorial is less than or equal to 1 over n squared. for all n greater than or equal to 0, 1, 2, 3, 4. And I can use a direct comparison test then to say that this is my AN and this is my BN, and BN converges by P series. AN is less than or equal to BN for all n greater than or equal to 4. BN converges by P series. So AN's series also converges by direct comparison test. And then I can say that the series converges absolutely because the absolute value of the series converged without having to test these conditions. Just this 1 over n factorial piece converged all on its own, so testing the conditions was not necessary this time. All right, let's look at 51. And 51 says n equals 2 to infinity, -1 to the n times n over n squared, n cubed minus 5. And I'm going to look at this piece, an equals n over n cubed minus 5, and this looks related to n over n cubed, which is 1 over n squared, which is a convergent P series. So I imagine this piece is going to converge on its own. I'll use the limit comparison test. Bn is 1 over n squared, which converges by P series, and limit as n goes to infinity of n over n cubed minus 5 divided by 1 over n squared is equal to limit as n goes to infinity of n cubed over n cubed minus 5 equals 1. So an and bn series both converge or both diverge. Then I have this statement right here that summation bn converges by P series. So then summation an also converges by limit comparison test, and then the series is absolutely convergent, meaning that the absolute value converged. All right, let's look at number 71. '71 asks us to determine the convergence or divergence of the series in question, n equals 1 to infinity, 8 over the cube root of n. That's going to be a divergent P series. Our P is equal to 1/3, which is less than 1. Really no work to show there other than that. 75 says summation from n equals 1 to infinity of 9/8 to the n is a divergent geometric series. R equals 9/8, which is greater than 1. 77 summation n equals 1 to infinity of 100 e to the negative n over 2. Now this isn't quite written as the geometric series the way that I want it, because I want the geometric series starting at 0. Same for the one above it, but I can still see what r is. R is equal to the square root r is equal to 1 over the square root of e. So let's rewrite here, n equals 1 to infinity of 100 times 1 over the square root of e raised to the n. And 1 over the square root of e is certainly between 0 and 1. So r equals 1 over the square root of e is less than 1, so this is a convergent geometric series. If I wanted to find what it actually converges to, then I would have to say 100 over square root of e over 1 minus 1 over the square root of e. I'd probably multiply by square root of e over square root of e and get 100 over the square root of e minus 1 and 100 over the square root of e minus 1. This is approximately 154.149 if I'm interested in what that converges to. All right, that's it for this video, and we'll come back next time and we'll talk about the ratio and root tests. See you for the next video.